This is a worksheet involving just a couple of more practice problems relevant for exam 3. First one involves this bicycle rider here. This might have been an old exam problem, I can't remember. Cyclist rides a bicycle with tires of outer radius 0.4 meters. She begins pedaling from rest at t=0 with constant acceleration so that after 9 seconds she's going 15 meters per second relative to the ground. If she looks down at the wheel at 0.5 seconds, what angular speed does she observe around the central hub of the wheel? To do this, we can figure out first of all what the linear acceleration is from the change in velocity over the change in time, right? If she's moving with constant acceleration, the average acceleration, which is delta Vx over delta t, is the same as the instantaneous acceleration, and that is 1.67 meters per second squared. And then we can figure out from that what the tangential acceleration of a point on the wheel is, and that is 4.167 radians per second squared. Again, probably the way I explain things in the videos, I would have done this a slightly different method. You'll get the same answer, but what you can do is figure out what from the given V final and V initial. So V initial is 0, V final is 15. We can figure out what omega final and omega initial are, and we can do that by using V axle equals R omega, right? So V axle final is 15, and we can figure out what omega final is, and omega initial is 0, and then we could directly calculate what alpha is by using delta omega over delta t. Very similarly, you get the same number. Once we found that angular acceleration, we can figure out what the omega is at any time using the constant alpha kinematics equation. If A is constant, then alpha will be constant. So in this case, omega equals omega 0 plus alpha t. We've got alpha. We want to know what omega final it has at time t equals 0.5 seconds, so I'm plugging in 0.5, and it started out at rest. So we get 2.03 radians per second. If the rider looks down at the wheel at 0.5 seconds, what is the magnitude of the total linear acceleration of a point on the outside of the tire she observed? So in this case, we need both the centripetal component of the acceleration and the tangential component of the acceleration, and we'll get the magnitude of the acceleration vector by taking the square root of the sum of the squares of those two components. And we already found the magnitude of the tangential component of the acceleration as 1.67 meters per second squared. The centripetal component of the acceleration from our formula that expresses the relationship between linear quantities and angular quantities, that was r omega squared. So at that 0.5 seconds, omega was 2.083, and therefore omega squared involves the square of that. So we can get these two components of the acceleration and take the square root of the sum of the squares to get the magnitude or length of that vector. Problem 2. 2 point masses sit at rest in outer space. They're lying on the x-axis. An astronaut swings a bat and strikes the 2 kilogram mass, causing it to move in the plus x direction at 20 meters per second. The bat is in contact with the 2 kilogram mass for 0.1 seconds. Later, the 2 kilogram mass strikes the 1 kilogram mass, and they stick together, moving as a unit thereafter. Find the magnitude of the average force that the bat exerts on the 2 kilogram mass during the 0.1 second hit. So here we can get that from the change in momentum using the net impulse delivered to the mass is equal to the change in momentum of the mass, and then if we call the x direction the direction that it's hit in, the x impulse, net impulse, is just equal to the impulse from the bat. That's the only thing exerting an impulse on it or delivering one to it. And that is equal to the average force from the bat times the time that it took to change its momentum. That is equal to the change in the x momentum of the mass, and that is 40 kilogram meters per second here. So we take this equation that I circled right there and solve for the average x component of the force from the bat, and we get 400 newtons. Find the speed of the stuck together balls after they collide. So the two stick together like they're covered in Velcro. And to find that out, we're going to use conservation of momentum for this completely inelastic collision. Originally, the 2 kilogram mass is moving at 20 meters per second, and then at the end, the combined 3 kilogram mass object is moving at some unknown final x velocity, and we can solve for that as 13.33 meters per second. C. How much kinetic energy was lost in the subsequent collision of the two masses? Well, the kinetic energy that's lost is equal to the initial kinetic energy minus the final kinetic energy. So that's 1/2 mv squared for just the 2 kilogram mass and its initial speed, and then 1/2 mv squared for the final mass and its final speed. And when we do that, we get 133.3 joules of kinetic energy that's lost. 3. Here's an object that is a 3 kilogram uniform disk of radius 0.5 meters, pivoted at the center, and it also has a 4 kilogram 1 meter long rod glued to the disk with one end at the disk's center. So you have to look at the figure to kind of see what the object looks like. The pivot allows frictionless rotation of the combined object in a vertical plane. It is initially oriented so that the rod is at its highest position as shown, and released from rest. A tiny imbalance makes the system rotate to the right. Find the angular acceleration of the object and the speed of the outer tip of the rod when the object has rotated by 45 degrees away from the vertical. So we want its angular acceleration when it's here. That's the first thing that's asked. And we can use torque net equals I alpha when the rod is aimed up in that direction. The net torque, well, there's a gravitational torque on the disk itself, which is 0, because gravity is not trying to rotate the disk in one direction or the other. But when the rod is over here, gravity is trying to rotate the rod down in that direction. So we can just use the net torque is just the torque being applied to the rod only. Rod's mass is 4 kilograms, so that 4 times 9.8 is as if it's being applied at this point going straight down. And the moment arm there is 0.5 meters times the sine of 45 degrees, this distance right there. So force times moment arm gives the net torque, which is just the torque on the rod part. And that's equal to the moment of inertia of the combined object times alpha. To get the moment of inertia of the combined object, we have to add the moments of inertia of the disk about its center plus the rod about the center of the disk. And that's, we have to look up in the table of moments of inertia. The disk about its center is 1/2 mr squared, and a rod about one end is 1/3 ml squared. Our rod is length 1 meter. The radius of the disk is 1/2 meter. So you add those together, 1.7083 kilogram meters per second squared. Kilogram meters squared. Plug in that number here, torque net equals I alpha, and solve for alpha. So as it passes this point, it's angularly accelerating at 8.113 radians per second squared. Now, to figure out the angular speed at that point, we can't use kinematics because the angular acceleration is 0 up here. It's getting bigger, 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 and so angular acceleration is not constant. We can't use our constant alpha kinematics equations. So we use the usual thing, which is take our combined object plus the Earth, with gravity being an internal force, to be our system. The only external force applying force on this is the force from the axis pin. It does 0 work because the point at which the force is being applied is not moving through space. So the net work done by all external forces is equal to 0. That's equal to change in kinetic energy plus the change in potential energy. Change in kinetic energy, we just use 1/2 I omega squared because it's a rigid object rotating around a fixed axis. So we don't have that extra term in here. That's only for rolling without slipping. So 1/2 I omega final squared minus 1/2 I omega initial squared, but that second one is 0, so I left it out of this equation. And then the change in potential energy of this object, the disk itself doesn't change potential energy, but the rod does, right? The rod's center of mass is originally up here, and then it ends up down there. So how far did it go down? Well, it was originally 0.5 meters above the pin, and then it ends up a distance 0.5 times the cosine of 45 above the pin. So if we take the difference between those two, 0.5 minus 0.5 cosine 45, that's how far it fell. And then we do mg, the mass of the rod, m, g times that distance with a minus sign in front of it because the change in the y-coordinate is negative. Okay, putting all that together, we're able to solve for omega final. That's the final angular velocity when it's in this configuration, and then we can use v equals r omega to figure out, let's read the question carefully, the speed of the outer tip of the rod when the object has rotated. So we want to know how fast this point right here is rotating. And so the relevant r is 1 meter. So we use v equals r omega, 1 meter times the omega we just got to get 2.592 meters per second. The speed of the tip of the rod as it zooms past this point out here. All right.